Hello, welcome to another video of Dr. Viv's. In this, we shall be talking about the problem of a smooth bead sliding down a helix, also known as a spiral, under the action of constant gravity. So the spiral itself is provided by the parametric coordinates indicated here. R is a cosine theta I hat plus a sine theta j hat plus b theta k hat. We are asked to determine the equation of motion of the bead with respect to time. That is to say, r is a function of time. Now the bead is going to be on the spiral at any given time, but we want to find out where on the spiral it's going to be. So that's why I wrote r as a function of time. We have to find constraint forces in both right cylindrical and Cartesian coordinates, and how are they related. Right cylindrical coordinates, by the way, are the proper coordinates to do this problem because the helix can be drawn on the surface of a cylinder. So the constraint forces in the cylindrical coordinate system can be converted to the Cartesian coordinate system, and then we can find the relationship between them. Repeat the same thing with the Hamiltonian approach, discuss the similarities and differences. So that's the problem. Let's start by drawing a helix. When I leave gaps, it means it's going behind. The separation is controlled by the parameter b, also called the pitch of the helix. We are going to take a coordinate system in which the xy plane is somewhere on the top, and the potential will be 0 there for gravity. And then the bead is going to be at some z coordinate below the xy plane. So let me draw the bead. Choose a different color, like that. So that's the bead. It's moving without any friction, like that. So there's the helix continues in both directions. Now we're not given any initial conditions, so we'll deal with that at the appropriate time. Our equations are as follows. R of theta is a cosine theta I hat plus a sine theta j hat plus b theta k hat. That's the equation of the helix. Now, even though I didn't ask you how to do it, it's pretty obvious. We have to use a Lagrangian approach because the Lagrangian approach is the only approach that gives you constraint. That was one of the reasons why Lagrange even started. People like D'Alembert and Lagrange started the program after Newton. Even though Newton was very smart, even during Newton's lifetime, people were starting to talk and saying things like, his program is pretty limited because it does not give you constraints. And then the rest of this course is about what people did to improve Newton's program. Now, we can write an obvious relationship between the x and the y coordinate. If you look at this, a cosine theta, a sine theta. So x squared plus y squared must be equal to a squared. But x squared plus y squared is also r squared in the coordinate system where you have r, you have theta, and you have z. R theta z is the polar coordinate system. So in that coordinate system, that is r squared. Let's write our two constraints. Our two constraints in the r theta z coordinate system are going to be r has to be equal to a. That tells you the spiral is going to occur on the surface of a cylinder. And then the second one tells you about the pitch of the helix. So r theta z is equal to z minus b theta, and that's also equal to 0. So that tells you that z must be equal to b theta. The Lagrangian, according to Lagrange's program, you first form the Lagrangian, which is the difference between the kinetic and the potential energy term. And then you can write down Lagrange's equations. Those equations are the following. d by dt, del L by del Qi dot minus del L by del Qi plus lambda j del Gj by del Qi equals 0. Here, I'm following Einstein's summation convention. So you're summing over all the j values. J in this case is a number of constraints. So in our problem, j will be 1 and 2. So this will have two terms in each of the Lagrange's equations. I refers to the generalized coordinates. So Qi's are called generalized coordinates. Qi dot are called generalized velocities. And this here is the negative of the constraint forces in the ith direction. So when we have to find the constraint forces, we can find them. All right, now let's get moving on this problem. The first thing we have to do is to find the kinetic energy term T. So that is done as follows. You take the kinetic energy always in Cartesian coordinates and see what has to be done to it in the new coordinate system. So that's x dot squared plus y dot squared plus z dot squared in Cartesian. In Cartesian coordinate system, you write x equals r cosine theta, y equals r sine theta, and z equals z. Now we are talking about the general relationship between Cartesian and right cylindrical. So when I differentiate both sides with respect to time, I can use the product rule because r and theta are both functions of time. So I get r dot cosine theta minus r sine theta theta dot. And y dot is going to give me r dot sine theta plus r cosine theta theta dot. Z will not change in the right cylindrical system. Now all I have to do is substitute x dot and y dot and square them and add everything together. So let me do that algebra next. T will be equal to 1/2 m. Square all this. So I get r dot squared cosine squared theta minus 2 r dot r theta dot cosine theta sine theta plus r squared sine squared theta theta dot squared. Okay, that's just using the a squared, a plus b whole squared formula. And then likewise, I do the same thing here. So I get r dot squared sine squared theta plus 2 r dot r theta dot sine theta cosine theta plus r squared cosine squared theta theta dot squared. And then last term is z dot squared, which stays as it is. Observe the beauty. These two terms, the cross terms, cancel out. Those are the troublemakers potentially. They cancel out. So now you just have sine squared plus cosine squared, which is 1, both here and here. And so our equation starts to look really simple. The kinetic energy term, T, is 1/2 m r dot squared plus r squared theta dot squared plus z dot squared. Now the Lagrangian can be written. Before we do that, we have to find the potential energy term. Now remember, the bead is going below the xy plane by our choice of the coordinate system. So the potential energy is going to be negative mgz because z is going to be less than 0 when it's below. But because of this negative sign, that becomes positive mgz. So the Lagrangian L is t minus v, which is 1/2 m r dot squared plus r squared theta dot squared plus z dot squared plus mgz. Now all we would have to do is implement this Lagrange program for each of the generalized coordinates qi. So let's take the r equation. I'm going to get d by dt del L over del R dot minus del L over del R plus lambda 1 del G1 over del R, that's what I'm doing there, plus lambda 2 del G2 over del R equals 0. Observe the denominator tells you which equation it is. The numerator tells you which constraint it is. Because there are only 2 constraints, you only have 2 terms. If there are 3 constraints, there'll be 3 such terms, including lambda 3. But here you have just 2 constraints. Let's do this step by step. So that's d by dt. When I take the derivative with respect to r dot, I just get m r dot because the 2 r dot that I get there will cancel with the 1/2. So that gives me m r dot minus del L by del R. Again, I get 2r there, which cancels with a 2. So I get mr theta dot squared plus lambda 1 times del G1 over del R is just 1 plus lambda 2 times del G2 over del R. There's no R at all. So that's 0. So I get m r double dot minus m r theta dot squared plus lambda 1 is equal to 0. Now I'll put r equals a. This advises me that I am going to be on the cylinder, not yet the helix, but on the cylinder. So that tells me that r dot equals 0 and r double dot is also 0. So that goes away. And so I'm going to get negative ma, because r is equal to a, theta dot squared plus lambda 1 is equal to 0. That's my first equation. All right. Our next equation is a theta equation. Well, that's going to be d by dt del L by del theta dot minus del L by del theta. So one of the pleasant aspects about this whole thing is it becomes automatic after a while. Del G1 by del theta plus lambda 2 del G2 by del theta is equal to 0. Let's do this. Del L by del theta dot is going to be r squared theta dot, because the 2 that comes from 2 theta dot again gets cancelled. So that's m r squared theta dot minus del L over del theta. There is no theta term. Plus lambda 1 times del G1 over del theta, that's 0. Plus lambda 2 times del G2 over del theta, that's negative b. And all that must be 0. Now this is where it's very important to do these things step by step, because d by dt will have 2 terms now, one from r and one from theta, because both of them potentially change with time. So that's 2m r dot theta dot plus m r squared theta double dot minus b times lambda 2 equals 0. Well, actually, r does not change with time. We are on the cylinder, so let's implement the cylinder condition, we are still not talking about a spiral yet. We are still simply on the cylinder. So r dot is equal to 0. And that gives me m a squared. The first term disappears because r dot is 0. And here I get a squared instead of r squared. Theta double dot minus b lambda 2 equals 0. Very useful looking equations already. The last equation is the z equation. That is d by dt del L by del z dot minus del L by del z plus lambda 1 del G1 by del Z plus lambda 2 del G2 by del Z equals 0. The first term is, that's our Lagrangian there. The Z dot term is over there. So I get 2 Z dot, which cancels with a 2. So that's just mz dot. And I differentiate this with respect to t. I get mz double dot. Then del L by del Z. Finally, we have something here. That's negative mg plus lambda 1 times no involvement of z. So that's 0. Lambda 2 does involve z. So I get 1, 0. So then let us simplify this. We have to use the second constraint. The second constraint is that z equals b theta. So I'm going to use that in the last equation here. G2 equals 0 tells me that z equals b theta. That tells me also that z dot is b theta dot and z double dot is b theta double dot. So I can write, instead of z double dot, I can write m times b theta double dot minus mg plus lambda 2 equal to 0. That's going to be my third equation. Equations 1, 2, and 3 have to be solved to solve our problem. I can already see that there's a very close relationship between these two equations. So what I'll do is I'll solve this equation for lambda 2. So I'm going to get from equation 2, I'll get lambda 2 equals ma squared theta double dot divided by b. And then I can substitute that into equation 3. Put into 3. So that gives me mb theta double dot minus mg plus ma squared theta double dot divided by b equal to 0. Now what I'll do is I'll multiply the whole equation through by b. So get rid of this b in the denominator. So I get mb squared theta double dot minus mgb plus ma squared theta double dot equals 0. Well, that looks really pretty. I can combine the theta double dot terms together. So that gives me m. First of all, you notice the m cancels out. So this is like Galileo's experiment. The mass cancels out. If Galileo had gone to the interior of the Leaning Tower of Pisa, assuming it was not leaning that much, and dropped two different masses on the banister of the staircase, he would have found that they also arrived down at the same time. So I'll call this the sliding banister Galileo theorem. So I'm going to get a squared plus b squared times theta double dot equals GB. And now I can solve for theta double dot. It's GB over a squared plus b squared. That's amazing. out of nothing, we've been able to solve for the acceleration of the bead. Now, let us further solve this. You integrate this once, so I'm going to get theta dot is equal to GBT over a squared plus b squared plus some initial value, theta dot naught, which we don't know, so we'll keep it as an initial condition. And then when you integrate it again, I get theta equals 1/2 GBT squared over a squared plus b squared plus theta dot naught t plus theta naught. So I'll indicate that here. You determine these from the initial conditions. I've indicated theta naught as theta at time 0 and theta dot naught as theta dot at time 0. If we are told that initially I see the bead at some angle of some radians and it's moving at a certain radians per second, then we have values for these. If we are not told, then we just keep them as constants. So this answers the first part of our problem. We have actually finished part 1 of our problem. So let's write down the answer. R as a function of t is going to be a cosine that plus a sine and then b has got where is that? It's just b theta. So for b, I'll just write b times all of this. Okay, should I box this? Maybe. So we have finished an important part of our exercise. Our next mission is to find the constraint forces. Remember, I told you the constraint forces are none other than those lambdas, the Lagrange multipliers written in that fashion. So let's do that next. So I can write negative f sub r is lambda 1 del g1 by del r plus lambda 2 del g2 by del r. Using that. G1 is right there. G2 has no r in it, so that's 0. Del G1 by del r is just 1. So I get f sub r is just minus lambda 1. But lambda 1 is right here. So lambda 1, negative lambda 1 is going to be actually equal to negative ma theta dot squared. So I can write f sub r equals negative ma and copy the result for theta dot from my integration right there. So it's GBT over a squared plus b squared plus theta dot naught. I'm actually going to be more interested in saving this result, so I'll call this result star. I will nonetheless box this. It reveals that the constraint force in the radial direction is time dependent. That makes sense because as the particle slides down faster and faster, the centrifugal force will increase. And that F sub r is precisely the centrifugal force. Now we do the next one, which is F theta. Negative F theta is lambda 1 del G1 by del theta plus lambda 2 del G2 by del theta. Well, G1 has no theta in it. So I'm going to get 0 there. Del G2 by del theta is just minus b. So keep that in mind. So that gives me negative lambda 2 times b. However, lambda 2 was right here. Lambda 2 was precisely that. So lambda 2 times b is going to be ma squared theta double dot. So I have f theta is equal to ma squared theta double dot. I'm going to call this equation double star because this is what I'll actually be needing for the transformation from Cartesian to polar. Now let us substitute for this. Theta double dot is just that. So I'll substitute and write it as m a squared gb over a squared plus b squared. So this is not dependent on time. It's constant. The last constraint is the z. So the constraint force in the z direction is lambda 1 del g1 by del z plus lambda 2 del g2 by del z. Now g1 by del z, there is no such term. G2 by del z is just 1. So this is just lambda 2. Therefore, Fz is lambda 2. But lambda 2 is precisely ma squared theta double dot over b. So, I'm sorry, it's minus lambda 2. So that's going to be minus ma squared theta double dot over b. And theta double dot is right here. If I cancel out the b's, I lose that b on numerator. And so I just get negative ga squared over a squared plus b squared. And that is Fz. As you can see, that also is time independent. So these two are time independent. Now we have been asked to ferret out the meaning behind the relationship between the Cartesian and the right cylindrical coordinates, how they are related, the constraint forces. So for that, we have to resolve the problem in Cartesian coordinates. It's not that bad, but I'll go through it a little bit quicker. So we're going to resolve the entire problem using Cartesian coordinates next. Things are actually simpler in Cartesian coordinates. So let's do this. First of all, the constraints. Now, when you go back to the original equation, the constraints, that is x, that is y, and that is z. So in Cartesian, you're going to have 3 constraints. I'll still call them G1, G2, and G3. But now They are functions of x, y, and z. So that's x minus a cosine theta, and that's equal to 0. G2 xyz is y minus a sine theta, and that's equal to 0. And G3 of xyz is z minus b theta, and that's 0. That used to be our previous G2, okay? But now it's G3. So we're going to write the Lagrangian down. Lagrangian is pretty simple. L equals t minus v, and that's 1/2 m x dot squared plus y dot squared plus z dot squared plus mgz. Now we'll write the x equation down. The x equation is mx double dot plus, there's no term involving x in the Lagrangian, so I just have lambda 1 times del L by del x, del G1 by del x, that's just 1, equals 0. So this immediately tells me that the first constraint force is mx double dot. So that's interesting, that's your fx. Let's find out what x double dot is. So that'll be our approach to do the constraint forces. X double dot is what? Well, first of all, x is equal to a cosine theta from the first constraint. So I get x equals a cosine theta. When I differentiate it, I'm going to get x dot equals negative a sine theta, theta dot. And when I differentiate this again, I get x double dot equals negative a cosine theta, theta dot squared, minus a sine theta, theta double dot. All right. So I'm going to write f sub x as m times x double dot, which is, there's an a common to both terms, so it's ma times, I'll write the sine theta term first, negative sine theta, theta double dot, negative cosine theta, theta dot squared. Let's just leave it like that. Okay. Now I'm going to move on to the y equation. We're not going to bother with the z equation because it's already in Cartesian form. When I do the y equation, I'm going to get my double dot. There is again no term in the Lagrangian with y, so that term vanishes. And then when you do the constraints, I only get a contribution from lambda 2 plus lambda 2 times del g2 over del y, which is 1. So that's equal to 0. And so that tells me that negative lambda 2 is my double dot, and that is going to be my constraint force f sub y, because negative of the constraint force is precisely that. So that's good. Now we have to just evaluate what y double dot is. From the constraint equation, y is equal to, so y double dot is how much? So y equals a sine theta. We'll differentiate the constraint equation. So I get y dot equals a cosine theta d theta by dt. And then y double dot is going to be negative a sine theta, theta dot squared, plus a cosine theta, theta double dot. And that times m is what f sub y is. So f sub y equals ma, and then I'll write the theta double dot term first, cosine theta, theta double dot, minus sine theta, theta dot squared. What I would like now to do is to compare this with the equations I called star and double star. I wanted to focus on them for a reason, because if you look at this, I get ma theta dot squared. So I can now try to replace these two equations with star and double star. Let me do that. I'll use a different color for this one. So fx is going to be ma MA times theta double dot. That's going to be F theta. So that's going to be negative sine theta, F theta. And then FR is negative MA cosine theta dot squared. So that's going to take care of the negative sign there. So plus cosine theta FR. And then Fy, this one, I have MA squared theta double dot. I don't have an A squared. So I'm going to divide both sides by A. Okay, so this gives me cosine theta F theta divided by A. And then theta dot squared with a negative sign is a plus sine theta FR. And by the way, I have to do the same thing here. When I identified theta double dot, it's F theta over A there also. So now I have my transformation equations I seek. I hope you're seeing the pattern here. These are nothing more than rotations. So I can write this in matrix form to identify what's happening. I'm going to write this in matrix form. So Fx, Fy, the constraint forces Fx and Fy are given by cosine theta, negative sine theta, sine theta, cosine theta of Fr and F theta divided by A. So you can see how this works. Fr times cosine theta minus sine theta times, so that gives you the first equation, and then second equation is got like that. So this is just a rotation by minus theta times the constraints in the polar form. I call this polar form of the constraint column vector. So the Cartesian form of the constraint column vector is just a rotation by minus theta times polar form. The other direction is very obvious because all you've got to do is change the direction of rotation to be positive. So the other transformation, FR, if I want to go from FR to F theta, how do I do that? From there to Cartesian, I just do the change the angle by negative. So I get sine theta, negative sine theta. So I just change theta to minus theta and I get my other transformation. So I can go from Cartesian to polar also. So that answers that question. Our last question in this video has to do with Hamiltonians. So to do the Hamiltonians, we have to find what is known as the minimal Lagrangian. So that's the program initiated by Hamilton. So let's do the minimal Lagrangian. Right away, you see that when you incorporate the constraints to form the minimal Lagrangian, you will lose all information about the constraint forces. Hopefully, the Hamiltonian approach will give us something back for all that loss. Let's see what that new information you get would be. So the constraints, I put that sheet back there so you can see what the procedure is going to be. Lagrangian L, the non-minimal Lagrangian, which actually was over here, is 1/2 m r dot squared plus r squared theta dot squared plus z dot squared plus mgz. Now what I will do is use the constraints g1 and G2. So we're back to G1 and G2 now. So G1 r theta z, which is z minus a, is equal to 0. Well, that tells me, well, r minus a, sorry, r minus a equal to 0. That tells me that r equals a and r dot equals 0. So I'm incorporating the constraints right away. G2 of r theta z tells me that z minus b theta must be equal to 0, which tells me that z is equal to b theta. And that also tells me that z dot equals b theta dot. Now I'm going to put these into the Lagrangian and make it the so-called minimal Lagrangian. So L min is equal to 1/2 m. R dot is 0, so that's 0 squared. And R is a, so that's a squared, theta dot squared. And z dot is b theta dot, b squared, theta dot squared. Well, ring a bell, a squared plus b squared. We are back to our famous a squared plus b squared term. So we are seeing that coming already at the Lagrangian level itself. And then the potential energy term is mg, but this time instead of z, I write b theta. What I've done, I've now made the Lagrangian minimal. Now I don't need these sheets, so I'll take them away. That is our minimal Lagrangian. So let me write it again. L min is now a function just of theta and theta dot. Observe, it does not depend on time. So that's an important observation. So I get 1/2 m a squared plus b squared, theta dot squared, plus mgb theta. Now we are free to form the Hamiltonian. The Hamiltonian is formed by some stages. So let's go through those stages. What we have to do is first find the canonical momentum. In this case, it's the angular momentum, so I'll write angular momentum. Well, that's p theta, which is the derivative of the Lagrangian, L min, with respect to theta dot. When I take the derivative, I just get 2 theta dot, which cancels with the 2 here. So I get m times a squared plus b squared theta dot. Now we have to do the Legendre transformation. What that tells you is solving for theta dot in terms of t. In this case, the Legendre transformation is simply dividing both sides by a constant. The Hamiltonian, theta, p theta, and a function of time, generally speaking, is going to be the sum over all the i's of pi qi dot minus a Lagrangian L written as a function of qi dot and t, where the qi dots are written entirely in terms of pi. So that's the way we do it. So let's write this. There's only one canonical momentum, so that's p theta, theta dot, written entirely as p theta minus L of theta, theta dot, written entirely as p theta, comma t. But you notice that the Hamiltonian does in fact not contain time. So the Hamiltonian will not contain any time. This is actually a theorem in Hamiltonian dynamics. It tells you that dE by dt is 0 or the energy is conserved. Something you suspect in the problem of a smooth bead sliding down a spiral. You suspect that's true. And Hamiltonian mechanics assures you that's true. So now let's form the Hamiltonian. H equals, that's going to be, when I put for theta dot, I get p theta squared over m times a squared plus b squared minus the Lagrangian, which is this. So I get 1/2 m a squared plus b squared theta dot squared. So when I square that, I get p theta squared over m squared a squared plus b squared, the whole thing squared, minus mgb theta. So for most simple cases, that's always 1 minus half the same thing. There are complicated cases where that's not true, so it's always wise to go through this each time. Minus mgb theta. So that's the Hamiltonian. Now we can write Hamilton's equations. You all know the drill. The first half of Hamilton's equations reproduces the Legendre transformation, and the second half gives you the dynamics. I'll stop when something familiar results, because Hamiltonian methods is going to give us the same information. So the first equation, Hamilton's equation, is theta dot equals del H by del P theta. Well, if I take the derivative with respect to P theta, I'm just going to get P theta divided by m a squared plus b squared. So that gives you our Legendre transformation back. That's great. Let's actually solve this. This tells me that P theta equals m times a squared plus b squared theta dot. And let's take a derivative for future reference. This gives me m a squared plus b squared theta double dot. Now we'll move on to the second set of Hamilton's equations, and that is P theta dot equals negative del H by del theta. If you look at this, there's only one term, and because I have the negative sign there, that negative sign goes away, and I just get mgb. But P theta dot is precisely that. So that's equal to m a squared plus b squared theta double dot. Again, the mass cancels, so you have sliding down the banister Galileo, and this gives us theta double dot equals gb over a squared plus b squared. Now we are back to where we were in our earlier treatment, so I'm going to basically stop at this point. So I'll write etc. So we get back what we have. And the big disadvantage of this method is that you cannot get any information about the constraint forces. Constraint forces unknown because they have been incorporated into the Lagrangian. However, we get something in return, and that is we do get the information that energy is conserved. So all is not negative in the Hamiltonian approach after all.